Hello, honorable chemists. It's Mr. VB here to talk to you about some calculations you'll need to do involving the lab assignment. Specifically, we're talking about sodium carbonate reacting with hydrochloric acid to yield carbon dioxide gas, among other things. Before we get started, though, let's write out a balanced chemical equation. We have almost ran out of room there. There's our balanced equation, but let's check it. We have two sodiums and two sodiums. We have one carbon and one carbon, three oxygens and 1, 2, 3 oxygens, two hydrogens, two hydrogens, two chlorines, two chlorines. So it looks like we're all balanced up and ready to go. So for my particular set of data, I'm going to assume that I massed out 0.97 grams of sodium carbonate to begin with. So in our case, we had a mass of the cup plus the powder of 4.11 grams. The mass of the empty cup was 3.14 grams. So if we subtract those numbers, we get 0.97 grams. So we start with 0.97 grams of sodium carbonate. Next we need to calculate, well, how many moles of sodium carbonate is that? And hang on and I'll go get my periodic table. Okay, I've got my periodic table. So we're going to need sodium. We have two sodiums. So for sodium, we'll have 2 times its atomic mass, which is 22.990 grams per mole. For carbon, we'll have 1 times its atomic mass, which is 12.011 grams per mole. And then for oxygen, we have 3 oxygens, so we'll have to have 3 times the atomic mass of oxygen, which is 15.999 grams per mole. And if I do the math, 2 times 22.990 plus 1 times 12.011 plus 3 times 15.999, I get the grand total of 105.988 grams per mole, which is the molar mass of sodium carbonate. Having got that far, now we need to know, well, let's convert 0.97 grams into moles. So to do that, we put 0.97 grams of sodium carbonate times 1 mole per 105.988 grams. Well, grams cancels with grams, and we're left with moles of sodium carbonate. And if I do that division, I will get 0.009152, and that is moles of sodium carbonate. Okay, so far so good. Now we need to convert that to moles of carbon dioxide that we would theoretically get. So what you'll notice here is the coefficient of sodium carbonate in the balanced equation is understood to be a 1, and likewise the coefficient of CO2 in the balanced equation is understood to be a 1. So there's a 1-to-1 correspondence between those two species. If I have 1 mole of sodium carbonate, I would expect to get 1 mole of CO2. If I have 0.009152 moles of sodium carbonate, I would expect to get 0.009152 moles of carbon dioxide. So let me clean up my whiteboard a little bit and give us some room, and then we'll proceed. Okay, let's actually show that conversion of moles of sodium carbonate to moles of CO2. Let's multiply that by the mole ratio, which would be 1 mole of CO2 for every 1 mole of sodium carbonate. Well, 1 over 1 is just 1, but what cancels? Moles of sodium carbonate, and we end up with our units being moles of CO2. Great, we're making great progress here. But now we've got moles of CO2. For our theoretical yield, we would like that to be grams of CO2, so we'll have to make that conversion. But first we need the molar mass of CO2. So for CO2, we're going to have carbon and 2 oxygens. Carbon, we're going to have 1 atom times 12.011 grams per mole. For oxygen, we're having 2 times the atomic mass of oxygen, which is 15.999 grams per mole. And if we add up those products, we get 44.009 grams of CO2 per mole. So that is the molar mass of CO2. 44.009 grams per mole. Okay, we know we have this many moles of CO2, and we know the molar mass now. So now we can say, oh, okay, 0.009152 mole CO2 times 44.009 grams per mole. Okay, moles cancels with moles. We end up with grams of CO2. So if we make this multiplication, we actually get 0.402769, which we'll call 0.40 grams of CO2. So what we've done so far is calculated the theoretical yield of CO2 for the equation, where we started with 0.97 grams of sodium carbonate. The theoretical yield is 0.40 grams of CO2. Now, what is our actual yield? Well, our actual yield we get experimentally by measuring the mass of all of our ingredients initially, and then taking that same mass again finally at the end of the experiment and taking the difference of those two. So for this fictitious data, my initial total mass was 54.50 grams. My final mass ended up being 54.18 grams. So if I subtract those, I know that 0.32 grams disappeared somewhere in the course of the reaction. And what that mass is that disappears, that's the mass of the CO2 gas that is produced and floats out through those holes in the saran wrap out into the atmosphere. So that explains our mass loss. We lost 0.32 grams during the experiment, and we presume that to be the mass of the CO2 that went out the plastic. So we have our theoretical yield of 0.40, our actual yield of 0.32. Now we can calculate a percent yield equal to our actual 0.32 grams divided by our theoretical 0.40 grams times 100. And for this data, which is fictitious by the way, this number ends up being 80%. So what we can say in conclusion is, using these data values, that in my case these are fictitious numbers, but the theoretical yield of CO2 was 80%.